Good morning, everyone. Hopefully you guys can hear me. A little higher. So my name is Raymond Calafon. I work in the Mechanical and Aerospace Engineering Department at UCSD. This is some joint work I did with Chuck Wells from OSI Soft. And we're particularly interested in looking at monitoring electricity grids. And I'll give you in this talk a little overview how much data that generates and what we do in terms of research. And mostly looking at distributed event detection and dynamic modeling. So before I go into, let me first talk about this technology. It's called PMUs, Phasor Measurement Units. They are being used a lot nowadays to actually monitor electricity grid. They basically measure voltage, current, angle, the difference between the current and the voltage. And the most important thing is it actually has a GPS clock on them. So it means that you can have these things distributed all over your electricity grid, and they monitor the data at a synchronized rate, which is very important when things go wrong. So yeah, there's this certain particular time accuracy. It's up to about a microsecond, and there's actually certain IEEE standards used to qualify and guarantee these things are working properly. And it's amazing. These things are being installed quite a bit. The United States has about 1,000 of them already installed. DOE has spent over $400 million in a particular project to install these things since 2009. China is installing them at about 2,000. And India, with their recent blackout, have decided that they also need them, 2,700. So a little closer to home, San Diego Gas and Electric has about 80 of them installed. They're mostly on distribution, about 100 seconds per substation. And San Diego Gas and Electric has special purpose PMU on the Palomar generation station. So what is the big deal here? Well, they generate a lot of data. And so the measurements are typically done at 60 hertz. There are about 14 channels per PMU. So if you do the calculations, it's over 800,000 samples per second being generated to monitor just electricity grid. So all nice and great, but what are we going to do with this data? Well, what will happen, events occur. And what are these events? This is a good example on the Western electricity grid. What I display here is the frequency, which should be around 60 hertz. And around 4 o'clock in the afternoon, a huge drop in the frequency indicated there was a huge power loss. And the grid oscillates. And the problem is that these things are too big or oscillate too much, the grid can actually shut off. You get a blackout. So question is, how do you detect these events? Remember, you have 800,000 samples coming in per second. How do you qualify them dynamically? And what do these events tell us about our microgrid? So what we do, and that's basically our contributions, and I'll show you a little example on this. We do two things for now. We look at some kind of a way to real-time detect these events instead of having to go through it by hand. Most of the people actually log the data and just look at it now to see what's going on. So, and when an event occurs, we look at the timing and then we characterize the event itself in terms of frequencies, damping, and modal participation. So it's a little different here in terms of maybe some of the other examples you see. It's a lot of dynamic analysis of the data. So we look at time dependency of the data and of course how these things are related to each other. So a little example of this, let me see, next slide, there you go, is I threw the slide in just to give you a little background. There's too much technical details, but basically the idea is we look at the ambient behavior of the grid, and based on the ambient behavior we decide how this grid behaves randomly, and based on the randomness we then decide, okay, if now something strange happens up to this randomness, that's an event that gets detected. And so we have developed some techniques to do this. A good example is, for instance, here, a little video of that same event. On the top, there's the actual randomness occurring, and suddenly the huge event occurs. And then the bottom, we create a so-called filtered rate of change signal that actually detects the event. And so what you see is there's a little event occurring once in a while, gets detected, and then when the big event occurs, multiple events occur, and that actually allows us to analyze the data afterwards. And so this is the event detection. So in this case, we were able to distinguish 14 different events, and this is about 900, almost 1 million data points generated over this nine-hour time frame. Now, how do we do that? How do we detect this event? Well, of course, you saw it before. You get a huge oscillation, and the oscillation is now characterized by a so-called method we call realization. And it allows you to reconstruct a model, which is here in the bottom left, that characterizes the dynamic response of that data. And with that model, we can now characterize frequencies, and damping. The frequencies are, of course, the oscillations you see. The damping tells you how fast the oscillation dies out. So instead of sending this raw data over to central servers, which is very hard to do if you have so many centers all over the country, you only send this kind of information, and when this occurred and how severe the event was. And it's a much better way of doing this data processing than sending all the data over simultaneously. Again, one slide on the approach. Again, too much technical details, but the main idea here is that there is some algorithm that we've developed that allows us to characterize this data and reduce it to a set of parameters that are interested for people that are monitoring the electricity grid. And the end result is really a dynamic model that we can use to simulate the data, but also analyze the data, and maybe even come up with mitigation strategies to get rid of these disturbances in the future. So a good example is, I like this example, this is an event that happened here at UCSD. We have a breaker, an SEL breaker, right on the 12 kilovolt line, and on the 9th of October there was a huge disturbance. We still don't know who that did this, but if you go to the next picture, there was 9 megawatts coming in, and there's a disturbance going down to almost 7 megawatts. So a huge disturbance here. Somebody turns off the air conditioning system in a building without everybody letting them know. And of course, it's very critical. The dampings estimated were almost 5%. So if this is too severe, it can actually shut off the grid here at UCSD. Breakers can actually shut off because of safety. And luckily, this didn't happen, but you can actually see the analysis we did here. And and this is a good example where this data analysis shows that an event occurs, we can actually pick those events up. And we also demonstrated, by the way, this is kind of interesting, with all these techniques you can actually come up with control strategies that if such an event happens next time, instead of having this blue line, you can mitigate it to the red line, which has a much better damping, by doing some controlled injection of power at the right moment. And you see that's very little, but it mitigates those disturbances. So my last slide to make sure I stay on time. So I think we do a good job so far and automatically detect when events occur, automatically estimate parameters that are relevant. The main feature is really this automatic detection and do things in real time. But there's still some challenges, and the challenges are really how do we do this in a distributed way? There's no way we can get all the data in a central server, do these computations. We like to do that on the sensors themselves, some distributed computing. And of course the data management and visualization. How do you distribute this information back to the end user, and how we're going to decide what to do with the electricity grid when these disturbances occur. And I'd like to leave it at there, to stay within my 7 minutes. Thank you.
We have time for one question. You can just yell it out, and then I'll try and repeat it for the video.
And I'll stick around if you guys have questions later on in the break.
Question here. So Raymond, with this modeling and compression, are you saying that the problem is no more one of big data, but big analysis?
I would think so, yeah. The problem here is that, think about it, you have 2,000, in this case, 2,000 sensors all over the country, and getting all the data into a central server, time synchronized to do this analysis, just an impossible task. I mean, just the Western electricity grids have a large issue with just getting 300 sensors out. So what we're thinking about doing the analysis locally and send only the analysis over. So I'm advocating to do this analysis in a distributed way. Put the analysis already on the sensors and send the relevant information, not the raw data. Now, I must say electricity companies are a little conservative and they like to have the real data, because liability issues. But that's fine, you can send it later. It doesn't have to be real time. So I'm hoping to solve the problem like that. No, thank you for the question.
Thanks. There doesn't seem to be, I mean, there's no indication before the event
that would be nice.
Going to happen.
Yeah.
But when you have enough events in different regions, presumably the prediction of the likelihood of when events would occur, you could potentially mine that data together.
That's right. So the way you see it is that we analyze the data and localize and classify it as events, and then you can put some machine learning on this. Okay, this event is happening all the time. Which person is constantly shutting off the air conditioning system at 9 o'clock in the morning, as an example. So that kind of stuff, you can use that for the analysis again. Yeah. So I can really see this as a data reduction technique to make sense of all this data coming in and see if there's any patterns. That's right. developers in a particular project to install these things since 2009. China is installing them at about 2,000. And India, with their recent blackout, have decided that they also need them, 2,700. So a little closer to home, San Diego Gas and Electric has about 80 of them installed. They're mostly on distribution, about 100. So yeah, there's this certain particular time accuracy. It's up to about a microsecond. And there's actually certain IEEE standards used to qualify and guarantee these things are working properly. And it's amazing. These things are being installed quite a bit. The United States has about 1,000 of them already installed. DOE has spent over $400 million interested in looking at monitoring electricity grids. And I'll give you in this talk a little overview how much data that generates and what we do in terms of research. And mostly looking at distributed event detection and dynamic modeling. So before I go into, let me first talk about this technology. It's called PMUs, Phasor Measurement Units. They are being used. Good morning, everyone. Hopefully you guys can hear me a little higher. So my name is Raymond Califon. I work in the Mechanical and Aerospace Engineering Department at UCSD. This is some joint work I did with Chuck Wells from OSI Soft. And we're particularly interested a lot nowadays to actually monitor electricity grid. They basically measure voltage, current, angle, the difference between the current and the voltage. And the most important thing is it actually has a GPS clock on them. So it means that you can have these things distributed all over your electricity grid, and they monitor the data at a synchronized rate, which is very important when things go wrong.